So now that we know the basics of how the algebra and the geometry of the complex numbers fit together, we want to get back to the idea of doing calculus with them because that was the original motivation here. That's what we're going to do with that algebra and geometry. So how do we define e to the alpha t, where alpha is some complex number? For example, even just defining e to the it, of course, would be a big deal and would probably be the crucial step. Okay. Well, and in particular, well, one thing that's strange about this, of course, is how could we have e an exponential, which we know is about continual growth? In fact, it's a very particular kind of growth, constant steady growth with a constant proportional growth rate, not a constant slope, but a constant y prime over y. How can we turn that into a circle? This doesn't seem the same, except, well, remember I did mention this is steady motion of a sort, okay? So this is constantly growing. Well, what is this doing constantly? It's constantly turning. And so somehow, oh, wait a minute, but I does have something to do with rotation. So, okay, this is starting to look plausible, okay? Well, we've got to actually look at a definition, and there's actually two. I'm actually going to do this backwards from how I have it in the PDF because I changed my mind in thinking about this. This is really number 10, but we'll go back to, I think I'm going to skip number 7 because it was extra, and I'll go back to number 8 and 9 later, okay? So here's one definition of e to the x. We have to actually go back and say, well, what the heck was e to the x anyway? What was the definition of that? Well, you can think of it as the number e raised to the power x, but that's actually one of the worst definitions, because how do you raise an irrational number to like another irrational number? It's complicated, right? But here's a really good definition. E to the x, well, really good sort of from intuition. It's not the best in terms of manipulation. And in problems 8 and 9, we'll go back to the one that's easier to prove things with. This is a great definition of e to the x. And let me remind you, at least this is the first place where my students see it. It's if you have principal p in an account that earns interest compounded continually, then the amount as time t is p times, well, what you do is you look at compound interest, which is you take the interest rate, and if you compound it a certain number of times per year, n times per year, you're going to earn that much interest each time, plus your principal, and then you're going to have n compounding periods times how many years it is. And then the cool thing is when you take the limit as n goes to infinity to represent continuous compounding. And this is a very famous formula, at least among my students and most high school students, PERT. Okay? And so this guy is turning out to be exactly the kind of expression we want, okay? Or to strip down to essentials, e to the x is a limit of this guy. And so what does that really say, okay? X is some medium-sized number, and we want to think of as really big because it's going off to infinity. So we take 1 plus a small number. So this is a very small growth factor, but a constant growth factor, and then we multiply that by itself many, many times, okay? And so, as I say in the PDF, the slogan for this would be maybe hugely repeated, that's the big N here, tiny scaling, which is the multiplying by 1 plus x over n. Hugely repeated tiny scaling. That is a good description of natural exponential growth, okay? Where the x tells you exactly how much the scaling is compared to how many times you repeat it. Okay, so, and of course, when x is positive, this is going to be a little bigger than 1, and it's going to grow. When x is negative, this is a little less than 1, and it's going to be decay. Okay, so what happens if we just put in like an it in there? Okay, so we'll look first at the case where it really is just I, because as I said, that's really the key. And we already know from everything we've got done, if this is going to work at all, and we're still trying to be hopeful about this, this should have a lot to do with circles. So there's a huge hint as to what should come out. But let's see if we can do it. Okay, and here is where we use the geometry of multiplication. Because all we're doing is we're starting with 1, and then we're multiplying repeatedly by a certain kind of complex number, which we can locate in the plane. Okay, so I'll go through the questions I ask in the PDF. A great place to stop and pause. Okay. So let's just be real simple to start with. T equals 1, n equals 10, say, just to get the idea. Okay, so let's look at what happens. What we're really interested in, we're interested in 1 plus t over 1 plus 1, sorry, 1 plus I over 10 to the 10th power. But let's just try and do that. Oh, let's make that a little bigger. Okay. We're going to start out at 1. And let's just multiply 1 plus I over 10 to the 1, then 2, then 3. Okay. And start with 0, which is just 1. Okay. Well, what does 1 plus I over 10 look like? It's going up a little bit. Okay. So 1 plus I over 10 is this arrow here. And that's it. We're done, if it's just the 1 power. Now we multiply it by itself. Okay. So this is where you can try to get this picture either freehand or do it out algebraically, or it's not bad to use a computer or a calculator that knows how to do complex numbers. But let's think about just doing it freehand. I want to multiply this by 1 plus I over 10. Well, I want to multiply this by itself. Okay. What happens when you multiply complex numbers? Okay. You're going to take this arrow and you're going to rotate it. Okay. How much are you going to rotate it? You're going to rotate it by this angle. Now you are going to scale it a little bit, but the magnitude of this guy, the magnitude of this sucker, 1 plus I over 10, is the square root of 1 plus 1/100th. It's the square root of 1.01. It's very, very close to 1. And, of course, eventually we're going to think about this being 100 or 1,000 or a million. This is basically 1. Okay, and that's going to be really important. So all that's going to happen is this angle is going to double. And we're going to be up here. And then the third power, we're going to be, the angle is going to double again. Now, realistically, this is a little bigger than 1, and so it's actually going to go out in kind of a spiral. But when this gets smaller and smaller and smaller, what we expect is it's actually going to go in a circle. So let's see what's happening. Multiplication by 1 plus a very small multiple of I is just a very small rotation. Okay, and let me emphasize exactly what's happening by looking at the difference of two of these vectors. Like this one, this was 1, 2, 3. This was like the third power, and this is the second power. What's the difference between those guys? It's this little arrow, and what is that coming from? It's coming from the I over 10 times, let's just call this z. This is the square power, we'll call that z. The difference is just coming from I over 10 times z. Well, that's just a very small version of z, make z small, and then rotate it 90 degrees. So let's think about what happens when you do that. I have an arrow anywhere in the plane. I make it much smaller. I rotate it 90 degrees, and then I add it in, because it's really 1 plus. I add it to z. Ooh. That just moves z perpendicular to itself a little bit. So here's z, here's I over 10z, and then here's the sum. Here's 1 plus I over 10 times z. And I'm just doing that repeatedly. So what I'm doing is I'm taking an arrow, moving it slightly perpendicular to itself, moving it slightly perpendicular to itself, moving it slightly perpendicular to itself. In the idealized version where those displacements are really, really tiny, that's just going to rotate the arrow. That's exactly how you rotate. Okay. So let's see. How do I ask it in the PDF? Okay. Yeah, what's happening geometrically? As n goes to infinity, it looks like I'm just moving perpendicular to itself. I'm taking this arrow and just going, and every stage, whatever it's at, I move it a little more perpendicular to itself. It gets over here, move it perpendicular to itself. What's the key fact about circles is that the tangent, the direction of motion along the circle, is exactly perpendicular to the radius. And the converse of that is that if you always move in a way such that you're moving perpendicular to your radial vector from a fixed point, you will traverse a circle around that point. Think if this is, this is like a sprinkler head or something, and you're trying to avoid the sprinkler, but you're trying to stay close to it. How do I move? I want to always move not going towards or away, but moving perpendicular to that radial vector. And if I do that always, I will trace out a circle. Okay, so as I ask in the PDF, if this motto was hugely repeated tiny scaling, then it's going to be hugely repeated tiny rotation, okay? Or moving perpendicular to yourself. Or in other words, it's going to be rotation in a circle. If you just always keep rotating on by little bits, you're going to rotate when you do the whole thing. Okay, so that was for IT over n, but it does give us, this is a great breakthrough because it's really saying there is a possible definition for e to the it, and it's doing what we want. At least we can pretty much convince ourselves it's doing what we want geometrically. So we're going to define, or one of the definitions could be e to the z is limit as n goes to infinity of 1 plus z over n to the n. And we totally know how to do that. This is just addition of complex numbers. It's scaling a complex number. And the cool thing is I'm not trying to define raising to some weird power. This is an integer. It just means repeated multiplication, like we were just doing. Okay, so that's going to be definition 1. Okay, it turns out that to do this more slickly and kind of be sure about these results, it's a little easier to use another definition. But this is really a great one to start with because it links very closely to the geometry. The other one's going to link more closely to derivatives and things like that, to the calculus. But we'll see that in the next video.